All right, welcome class to lecture 26. We have begun our discussion of nonlinear response statically, focusing in on phase transitions and its phenomenology. And most recently, last lecture, we have arrived at a theory of phase transitions of spontaneous symmetry breaking, first proposed by Landau, in which we envision describing phases by order parameters and then writing out simple free energy functionals which take in information about symmetry and the spatial variation of the field to give us really simple generic functional forms that are then amenable to analytic calculation. So specifically, last lecture, we were introduced into the Landau form for the free energy describing magnetization or Z2 symmetry breaking. Which we arrived at through an explicit coarse graining of the underlying Ising model we imagine is microscopically describing our system. That free energy functional or effective Hamiltonian generically as a function of phi is given by a sum of two terms. Let's give that an R dependence. It's an integral over all space. Some function f of r, which is local in space, and a term that knows about how phi changes through space, so-called squared gradient term. So this effective Hamiltonian is really a free energy. It is a potential that describes the statistics of the phi field. As a consequence, it depends not only on things like microscopic parameters like the couplings in the Ising model, but additionally could depend on thermodynamic state points like temperature. In fact, we'll show in a second that we parameterize this first term on the right-hand side, the local free energy function, can be thought of as a local free energy density. As I integrate it over all space, I will get the local contribution to the free energy. We'll parameterize it with a temperature dependence in order to describe a temperature-driven phase transition. And as discussed last lecture, this squared gradient term with the parameter gamma being positive, we called it gamma last lecture. I think through this lecture, we'll call it M. This squared gradient term, provided M is positive, which one takes it to be, is something which penalizes inhomogeneities. And thus acts to stabilize locally smooth functions of the order parameter. This is a necessary contribution in order to stabilize domains of the order parameter purified in one value over another. So we keep talking about order parameters. So that's what phi is playing the role of. Its job is to encode the distinguishing features between the phases we're interested in. So in an Ising model, in a theory of magnetization, this order parameter is the local magnetic moment. Absent that information, this is a generic theory for a phase transition that one would write down independent of the underlying notion that we have in our minds that this is meant to describe magnetization. This is a theory which could have described anything before I told you what that order parameter field was. When I tell you, however, what I mean by phi, what that does practically is determine the functional form that this local free energy density can satisfy, because it is envisioned as an expansion in phi whose terms depend on the symmetry of that order parameter. So when we write down this theory and we're imagining that this is describing a magnet, that phi is the local magnetization, we know that in the absence of an applied field, I have to have an even order in expansion in phi. Odd order terms must vanish by symmetry. We can provide coefficients to that even order expansion, canonically chosen to be A and U, where A is envisioned as being expanded itself to first order in the temperature difference near the critical temperature. And all the other parameters, C, U, and M, are positive. So we arrived at this theory explicitly by coarse graining the Ising model and making a couple founded approximations, namely that we were first only interested in larger length scale behavior that let us integrate out some of the small scale behavior of the system, providing us with a smooth field, something that didn't know about the discreteness of the underlying spin density. We envisioned that we were near the critical point, consistent with the notion of being interested only on large scale behavior, which allowed us to expand this local free energy density to some small order in phi, because near or exactly at the critical point, the average value of phi is 0. So we're imagining that we don't depart too far away from that average value. And thus phi is imagined to be small. And then we worked under the assumption that putting this theory on a larger length scale should allow us to consider only those slowest spatial modulations of the field, and thus we could truncate these spatial variational terms to low order, and assuming that the system was overall translationally invariant, the lowest order expansion is this squared gradient term. So in principle, one can arrive at this free energy functional through that sequence of approximations. However, in practice, this is not actually how it's done. Landau himself, when he wrote down this theory, wrote it down completely phenomenologically. He intuited the fact that if he had a free energy density of some order parameter, like magnetization, it would have to obey the symmetries of that underlying microscopic Hamiltonian. And then knew that a first order expansion in the variation was a gradient expansion, so just wrote it down similarly. In fact, often such Landau theories are written down completely phenomenologically. If you had a new phase transition that you wanted to understand, if you can identify a relevant order parameter, you can essentially jump to this step, understand for that given order parameter what the symmetry group might be, which informs what the expansion of the local free energy density is, which will necessarily have terms greater than harmonic terms to describe the nonlinear dependence of a field. And then depending on how rapidly varying you imagine the spatial ordering is, one might need to go to terms higher order in the gradient expansion. Indeed, we'll explore in our final week class next week other sorts of Landau theories for different phase transitions, which we'll be able to just write down phenomenologically, kind of understanding what these approximations were. And indeed, I alluded to the fact that if you actually study this Hamiltonian on the field, defined as a field theory, numerically exactly, that you do get exactly the right critical exponents. If you embed this field in 2 dimensions, you get the 2-dimensional Ising universality class exponents. If you embed it in 3 dimensions, the result is the same in that you get the correct 3-dimensional exponents. That must mean that there's a conservation of difficulty, and indeed, studying this theory exactly is just as difficult as studying the original Ising model. However, by nature of it being a field theory, we don't have to worry about the discreteness of individual states. And we have, over the course of this semester, built up analytical techniques to study field theories. And so even though it is just as difficult to solve exactly, it's much easier to understand the structure of approximate solutions. In last lecture, we gave one flavor of such an approximation if we noted that the partition function could be written as an integral over all realizations of the field, weighted by this effective Hamiltonian. Well, that's a path integral. Last lecture, we approximated this path integral with its saddle point. Where this special value of the field is that which minimizes the local free energy as determined through the functional derivative of our effective Hamiltonian. That turns into be exactly what you would find with a mean field theory. So it replaces and that should make sense, it replaces a thermally fluctuating field in which many different field configurations can contribute to the partition sum, and approximates it with one characteristic, typical or mean value of the field. When we did that, we found that, let's actually call this some average, now that we know that it really is the mean value of the field. If we did it in absence any boundary conditions that enforced us to have spatial variation in the field, that the average value was just a number, the same value through space, and that number was equal to 0 if t were greater than 0. Remember, T is the dimensionless temperature relative to the critical point. It endows the theory with a temperature dependence through this coefficient A, that if you are greater than the critical point, put in by hand that the average value of the field was 0. But below that, for T less than 0, we found, consistent with our expectation, a spontaneous symmetry breaking, where there were two equally likely solutions at plus or minus C times the reduced temperature over U. Those are two degenerate solutions. The system, being classical, will have to exist in one of those two solutions, and thus will choose spontaneously which to fall into. Repeated realizations of a quenching process, whereby we took the system at high temperature and cooled it down very quickly, would result in equal numbers of the positive phi state, the spin up state in the context of magnetization, or the negative phi state, the spin down realization for magnetization. Okay, so that's what we did last lecture. So we're going to do two things this lecture. First, we're going to talk about mean field theory slightly more carefully, understanding exactly what approximation we're making. That will help us identify how we correct mean field theory. Correcting it exactly makes our calculation intractable, so we'll figure out an approximate technique to correct mean field theory with, and understand the conditions over which that will be sufficient. Unfortunately, what we'll find is that mean field theory is always going to be invalid if you're looking close enough to the temperature for specific dimensionalities where fluctuations grow faster than the mean. So in the dimensionalities that we care about, 2 and 3, where phase transitions both exist and are physically realizable, mean field theory, while giving us a good approximation, a good phenomenological characterization of the theory, won't be quantitatively correct. And in fact, we'll see that fluctuations will always act to suppress the value of the critical temperature relative to what we would have expected at mean field. And they will do so in a way that depends on microscopic parameters. So having identified the corrections to mean field theory, which is the first goal of this lecture, will then show that quantities like the specific critical temperature are things which are really not universal. They depend fundamentally on microscopic parameters. And so we're really outside the scope of a phenomenological theory like this. So we'll find that with a fairly general calculation, which shows an internal consistency with the way we're describing the system in this field. Okay, so those are the two things we'll do. So let's go ahead and get started. So let's begin with reformulating mean field theory a little bit more carefully. So let's introduce a decomposition of our fluctuating field phi that has a mean component and a fluctuation about that mean. while we have an independent definition of the mean, it's going to be that which minimizes the effective Hamiltonian. This equation essentially provides a definition for the fluctuation. Within that decomposition, we can write out our effective Hamiltonian. So inserting phi decomposed into its mean and its fluctuation, we would find, let's remind ourselves of the explicit temperature dependence there. We would find a mean field part of the Hamiltonian. But in addition, putting in phi in these three places that it appears, in phi squared, phi 4, and the squared gradient term, just factoring all that out, we would get a quadratic term in the fluctuations. Plus a mixed term that went as phi bar squared fluctuations squared. So that's the full quadratic piece. We get a squared gradient of the fluctuations. And then we would have a fourth order term in the fluctuations. So we have explicitly dropped any term linear in delta phi. Because we know by construction, any linear term is going to average to 0. The average of a fluctuation is 0. If we assume, again, that we have no specific boundary conditions, the square gradient of the mean field is 0. The field is spatially homogeneous. We can identify this, the term that depends only on the powers of the mean field, as a mean field part of the Hamiltonian. And so everything else all of these terms are then a correction. It's really ugly. Let's get rid of that. Whoop. Let's define that as a correction beta delta Hamiltonian. So with that separation, we now have a Hamiltonian that has a mean field part, which depends on this average phi, which will minimize the Hamiltonian, plus a correction term that depends on the fluctuations of phi around that mean field. That separation lets us write down the partition function, which is a path integral over all fluctuating fields, weighted by the full Hamiltonian, into a mean field piece which I can take outside of the path integral because it is a single value of the field. It's not fluctuating. Phi is just a number times a path integral weighted by the fluctuation correction term. So we have, just as our decomposition of the Hamiltonian, we have a decomposition of the partition function into a mean field piece and a contribution due to fluctuations. In mean field theory, we assume that this is negligible. Just as our partition function is decomposed, so too is the free energy. So we have a mean field part of the free energy, which is just defined as minus kBt log the mean field partition function, which per unit volume obtained through integrals over the field points of the homogeneous value of the field phi, we recover just our local free energy function that we've put in. Where we could invoke self-consistency to say that the average value of the field, the value of phi that we're expanding around, is that which minimizes that free energy, which essentially defines what that value of the field is, or allows us to calculate it. Indeed, minimizing that effective Hamiltonian, we would find, as we did before, that when t is greater than 0, that average value of the field is 0. And when little t is negative, we spontaneously break symmetry. So just as before, we've gotten a mean field piece that qualitatively gives some good physics. It gives spontaneous symmetry breaking. It would provide critical exponents, mean field critical exponents, like the fact that the average value of the field below its critical temperature rises with T less Tc to the 1/2. So a critical exponent beta, which is 1/2, not quite exactly right. We discussed last lecture that the heat capacity is predicted to be discontinuous, which is not quite right, but we get a susceptibility that diverges, albeit with a critical exponent, which is also not quantitatively correct. But formulating mean field theory in this way lets us ask explicitly about what we've neglected, this beta delta H. So let's now ask about the fluctuations around the mean field, or specifically, acknowledge the fact that what we're missing are spatial variations of the field away from this average value, which contribute most significantly to the partition function, or therefore the free energy. So we know what the explicit terms are. They're all of these terms. All right, so that's the fluctuation correction term, whose statistics we would need to evaluate, whose contribution to the partition function we will need to evaluate in order to understand exactly where we've gone wrong, how we can make our estimate of critical exponents, etc., approach something more quantitatively correct. So if you look at this, we find that we have terms that go quadratically in delta phi, so that are harmonic fluctuations about the mean. But in addition, we have this fourth order term here in the second line. That's going to be really hard to work with. We should anticipate that. Let's, in order to understand the structure, write this down in Fourier space. We know that at least in Fourier space, the quadratic terms will be really simple. So introducing a delta phi hat of Q, we'll get our correction as an integral over Q, and a sum of terms that are quadratic and local in Q, and our fourth order term, which is still complicated in fourth order. All right, so we know that if we could solve this, if we could integrate these fluctuations exactly, we'll have solved the Eisen model, so we know that that's probably too hard. So let's make now an approximation that we include only Gaussian fluctuations about the mean field. So let's neglect this pesky fourth order term. If we neglect that, then look at the structure of the correction. It goes quadratically in delta phi hat of Q with an effective spring constant. Let's let, as we have before, it be denoted chi inverse. That chi inverse of Q is, as constructed, A of t plus 3u, the mean value of phi squared, plus mq squared chi upright. This is diagonal in Q, so it's easy to take that functional inverse. But we also know that if we invert it, that will give us the correlations of phi in Fourier space. So inverting this, we have a of t plus 3 average squared plus m q squared. So q, again, is a wave vector, has units of inverse length. We can make that length scale, we can make that term dimensionless by writing this as some prefactor at chi evaluated at zero wave vector, the zero wave vector limit, 1 plus a length scale c q squared. So there's a natural length that emerges, which tells us how fluctuations in Fourier space are peaked, or how fluctuations in real space are correlated. So this is a natural correlation length. If we go through and explicitly calculate from this expression right above what the form of this correlation length is, we get that it's going to depend on whether or not we're above or below the critical point, as it will depend on whether phi average is finite or zero. We know that phi average is 0 for t greater than 0 and is equal to ct minus over u square root of plus or minus. So plugging that in, we find that for t greater than 0, so for temperatures above the critical point, this correlation length goes like mc over little t to the 1/2. For temperatures less than the critical point, it will be equal to m over minus 2c little t square root of. And thus we found a diverging correlation length at the critical point. i.e., when little t is 0, it diverges like t to the minus 1/2. So we found another critical exponent, one which dictates the divergence of correlated fluctuations that scales with a critical exponent of 1/2. Indeed, this is something we anticipated in our phenomenological discussion of phase transitions, that the only way to get divergences in thermodynamic quantities like susceptibilities is if the system becomes correlated over macroscopic length scales. So we have just uncovered the specific temperature dependence of that correlation length. Again, we find something quantitatively inaccurate in a three-dimensional system that critical exponent should be 0.63. We found it's a value of 1/2 in this mean field theory. And further, that critical exponent dictating the divergence of correlations is phenomenologically observed to depend on the dimensionality, but we find no dimensionality here. There's no sense of the dimension of the space we've embedded this field in. Okay, so we've just found that this fluctuation correction is dependent on the correlation function, which is divergence. So that's going to be a bummer. That's going to start to reflect the fact that those are contributions that we're not going to be able to neglect. To understand this a bit better, it's worth thinking about chi not in Fourier space, but in real space. So chi of r in real space is a correlation function. Which correlates fluctuations in phi at some arbitrary origin with fluctuations at phi at some point r away from the origin. It is computable by an inverse Fourier transform of chi hat of q in d dimensions. We can write down a d-dimensional Fourier transform as an integral over the d-dimensional solid angle and an integral over the magnitude of that wave vector to the d-1. Specializing to 3 dimensions. We'll get one factor of the solid angle from some phi coordinate. We'll have our integral over q and an integral over some theta. This defines a spherical coordinate system in q space. Like so. So if we do the same trick we've done a number of times, or you've done a number of times in your homework, and point and choose the z value of q to lie along the theta is equal to 0 value, we can write this dot product entering into the Fourier transform as a product of the modulus of r and q and the cosine of some angle theta. That will allow us to, through a u substitution, integrate out the theta degree of freedom, leaving us with the 0 wave vector value of chi over 2 pi factors, 2 pi factors from the definition of the Fourier transform, a 1 over r and a dq q sine of q times r over 1 plus correlation length squared q squared. That's an integral that we can do. In fact, we've seen that exact integral before. We found that integral in our discussion of the Debye-Huckel theory. Indeed, doing that integral, we find a zero value chi naught, 4 pi over r, and a decaying exponential where we do in fact see that C sets the length of correlations. It is really a correlation length. So we find, interestingly, in 3 dimensions, a screamed Coulomb potential. What's interesting is that at the critical point, when little t is equal to 0, the correlation length diverges. E to the minus 1 over a divergence number is e to the 0, that's 1. So at the critical point, this correlation function decays like a power law, 1 over r. So while at any finite temperature not equal to the critical point, there are exponential correlations. Exactly at the critical point, there are algebraic correlations. This power law decay results in patterns of the phi field exactly at the critical point that are self-similar. There's no inherent length scale anymore because of the algebraic decay. You'd also call those patterns fractal. All right. It's hard to write this down in arbitrary d dimensions, but one can do it if you introduce some bit of abstraction. So in d dimensions, there's still a 0 value of chi. It will still decay algebraically to the d minus 2 with some function y scaled by the correlation length, where this y function is an integral over a dummy variable like the modulus of q, reflecting the modulus of q, and an integral over the solid angle. It's a modulus of q non-dimensionalized by the correlation length. In 2 dimensions, so in 3 dimensions, we found that this gives 1 over r decay at the critical point. In 2 dimensions, C of R will go logarithmically with R. Indeed, there's a good reason why you have this analogy with Coulombic systems. The squared gradient term that we have that introduces our notion of space is exactly that same functional form that you'd have in Poisson's equation. So fluctuations can screen those interactions away from the critical point, but at the critical point, you have scale-free behavior like you have in any second order ODE on a field. For that same reason, in 1D, C of R would go like R. Okay, so we've got a notion of correlations. We've got a notion of things that we're neglecting in our mean field treatment, which indeed are certainly representative of the fact that these contributions are going to be really large as we approach the critical point, as these correlations diverge or become increasingly large. A means of actually quantifying where the mean field approximation is at least internally consistent, where we can neglect the contributions from the fluctuations, was originally given by a student of Landau's, Ginsberg. I don't remember what Ginsberg's first name was. So we've got a means of approximating the scale of fluctuation. So let's ask explicitly, under what conditions are the fluctuations in the field small relative to the contributions of the field, the self-contributions squared? So those are terms that are kept in our mean field theory. Those are fluctuations that are neglected. So when this inequality holds, mean field theory will be accurate. And if we evaluate both of those in mean field, we can at least find a self-consistent expression that tells us within the theory itself, when is this a good approximation? So the term on the right we have an explicit expression for. Within mean field theory, this is just at least in the ordered state, minus A over U. It is exactly 0 in the disordered state, reflecting the fact that the disordered state we imagine is a vacuum state, doesn't have any interesting behavior. We noted that, we could have noted that, in fact, when we computed its heat capacity. Its heat capacity is 0. So it only makes sense to ask about this in the ordered state, so for t less than 0. So that's the contribution we've kept. We can estimate the fluctuations within our mean field theory by using that mean field correlation function we just identified. So specifically, if we were to integrate our correlation function over a volume set by the correlation length divided by that volume, that will give us the average scale of the correlated part of the field, averaged spatially. Generically, that integral will be something that depends on the prefactor of that correlation function, some dimensional dependent number, geometric value that depends on factors of pi for the specific solid angle we're evaluating. And we'll go like that correlation length to the d minus 2. That is because we know C of R is some decaying function to the R to the d minus 2. So doing a U substitution, factoring out the correlation length dependence, we have a value of the correlation length to the d, a value of the correlation length to the d. We're able to pull out just the correlation length then to the d minus 2. We found previously that our correlation length is equal to some bare correlation length times a divergent part, to the minus 1/2, where that bare correlation length is equal to m divided by c TC, the minus 1/2. We could factor out the divergent part from the non-divergent part. And so we can write this inequality just in terms of, so again, this is minus c t over u. Just in terms of these parameters are a's and u's, c's and t's, and m's. So for mean field theory to be internally consistent, we require that A over U is much, much greater than this dimension geometric factor AD minus twice A, the correlation length to the D minus 2. We can rewrite that as twice A squared divided by U M squared must be much, much greater than AD M squared D minus 2, taking a minus on both sides, moving one factor of A and multiplying both sides by M squared. a squared over m squared a squared over m squared is the correlation length squared, inverted. So that's the same as twice u, the correlation length squared, must be much, much greater than AD twice m squared, the correlation length to the d minus 2. Or localizing the correlation length over to the right, we get that the correlation length less its bare value, its bare value to the d minus 4 must be much, much greater than this geometric factor AD over the bare correlation length to the d times twice the change in the heat capacity if we remind ourselves that the change in the heat capacity from the previous lecture is equal to c squared over 4u times Tc. All right, so that's some manipulation to get a statement of the inequality that has physical interpretation. For mean field theory to be accurate, we require that the correlation length, the divergent part of the correlation length raised to the d minus 4 stays much, much greater than some number that depends on geometry of the space we're in, the change in the heat capacity, and the bare correlation length to the d. So note that that left-hand side depends strongly on dimensionality. For d greater than 4, as t goes to 0, the correlation length always diverges. But for t greater than 4, or for d greater than 4, that divergence actually saves mean field theory. The inequality is going to be valid. This is a statement that in high dimensions, the self terms grow faster than the correlated terms. And actually, you can get quantitative accuracy in mean field theory. We haven't discussed this. This is discussed in the intro class that I teach. But if you were to look at the Ising universality, universal exponents, critical exponents, for dimensions 4 and higher, mean field theory actually is quantitatively accurate. The mean field value of beta of 1/2 is what is observed numerically. Can't be experimentally because you can't study a 4-dimensional system experimentally. However, this also tells us for d less than 4, the fact that the correlation length diverges, now it would do so with a negative power, a negative exponent, means that it will, the left-hand side will be driven to 0, necessarily violating that inequality. So as we get close to the critical point, fluctuation corrections become increasingly important relative to the terms we've kept. One can define a temperature. So if you rewrote this in terms of a temperature instead of the correlation length, the divergent part of the correlation length is just T less TC over TC, square root of, that's taking D 4 minus D, dividing it by a half, that's the square root. We require that that is much, much larger than AD to the change in the heat capacity, the bare correlation length to the D. Indeed, for D is less than 4, that will be violated. You can define a temperature where it is saturated, call it Tg, and this is known as the Ginsburg temperature. That's the temperature beyond which mean field theory begins to break down. Phenomenologically, this is the temperature from which the system stops behaving like a mean field system. You can actually observe a deviation from critical exponents that look like their mean field values as you approach the critical point, up to this Ginsburg temperature where you start seeing non-mean field exponents taking over. How close you have to be depends on some microscopic parameters like this bare correlation length. Indeed, for systems that have very large bare correlation lengths, you can get actually very close to the critical temperature, relatively speaking, before observing a breakdown in mean field exponents. In fact, Landau first worked out this theory not for magnetization, but for superfluidity, to understand the superfluid transition in helium. Also for superconductivity. And in both of those systems, the bare correlation lengths are sufficiently large that it is experimentally intractable to actually observe deviations from mean field theory exponents. They should be there, but you have to get so close to the critical temperature that you can't actually observe the difference between their mean field theory exponents and what their exact fluctuation corrected exponents would be. That's essentially because what sets the bare correlation length in a superconductor is the coherence length, which is much, much larger than a unit cell, the other relevant length scale in the system. So by formulating mean field theory a little bit more exactly, we found criteria for which we know how far we can trust it, and in which cases it's going to be quantitatively valid. We can actually use this correction to understand how fluctuations change observable properties as well. Like, how do they correct for where the transition actually occurs. We put that in by hand when we parameterize that little a variable, which at mean field theory specifies where the critical transition occurs. In the exact theory, there's no guarantee that the value of the critical point we put in is where the actual system would transition between an ordered and disordered state. A nice way to actually show that is to write out the partition function exactly as its mean field value times its fluctuation correction. Let's define that part as QC. And if we treat the fluctuations as Gaussian, that's an integral we could actually do. QC would just be a path integral over the fluctuations of phi, e to the minus 1/2, if we wrote it in Fourier space, an integral over Fourier variables, fluctuation in phi squared and chi inverse of q. So those are a sequence of independent Gaussian variables for each Fourier mode. And we know how to do each one of those Gaussian integrals. That will give us a product over all q, 2 pi over chi inverse of q. Or, in terms of a free energy, we have our mean field free energy less 1/2. We can turn the log of a product into a sum, and in the infinite limit, that sum over Fourier modes becomes an integral. So we have an integral over q log of chi inverse of q. So chi itself, inverse of q, is a second derivative of the free energy. Right? It's a variance in q, which means that we could take that functional derivative on both sides and get chi inverse of q is equal to chi inverse of q evaluated in mean field plus 1/2 an integral over q chi upright, and the second order functional derivative of chi inverse of q so momentum conservation means that's just minus q. Like so. That functional inverse, hard to evaluate. But this gives us a self-consistent expression for chi. We have chi inverse on the left, chi inverse on the right under the integral. If we remember that the susceptibility, which chi is proportional to, at the critical point, chi diverges, which means that inverse chi goes to 0 at the actual value of the critical point. So let's define, that's at its zeroth mode, macroscopically, we find infinite order fluctuations. So we can define chi inverse evaluated at its zero mode as tau, which when tau is equal to 0 will report on the new fluctuation corrected critical point. So evaluating this equation here for Q is equal to 0, we find that tau is equal to the mean field value of chi at 0 is just A. We get a 6Q, because we know what that Gaussian correlation function is, an integral over Q, 1 over tau plus m Q squared. Setting tau to 0, to find the location of the critical point gives us an expression that A is equal to minus 6um an integral over 1 over Q squared. That's an integral over the vector Q, which can be interrogated. We'll get a factor of AD, those factors of pi is associated with the solid angle integrals, an integral over the magnitude of Q, Q to the D minus 1 over Q squared. Uh-oh. That whole thing so I have minus Q to the D minus 3, which does not look super regular. So in fact, in general, this is a divergent integral. We have to introduce a regularization if we evaluate this at some cutoff, call it lambda, we find that there is a depression in the critical point that is going to depend on precisely that value of that wave that wave vector cutoff. So specifically rewriting A in terms of little t and c, we find that the new value of the critical point is given by the old value of the critical point suppressed by some number which is greater than 1. So the new critical point is when we include fluctuations at Gaussian order that acts to depress the value of the critical point in a way that depends on this wave vector cutoff depends on the microscopic scale that we can go down to. So this calculation expresses the fact that the location of the critical point is intrinsically dependent on molecular details, on high wave vector physics, on specific interactions for which the spins or the molecules will interact by. The existence of critical scaling, of universal exponents, those are all independent of those molecular details. But there are quantitative properties like the location of the critical point that is going to be really hard to estimate, that we have to run back to molecular level details to understand. As d goes to infinity, that's a way of thinking about the mean field limit. We find that TC is given exactly by TC mean field, because 1 plus I think I must have. Right, we can take that wave vector cutoff arbitrarily small. However, for any d less than 2, for d is equal or less than 2, taking that wave vector cutoff arbitrarily can drive that critical point all the way to 0. All right, so we'll explore that a little bit more next lecture, and we'll also start generalizing this Landau theory to other sorts of phase transitions, including the liquid vapor transition, and then in the last lecture to ordering at finite wave vector, not infinite wave vector, in the context of block copolymers. So look forward for that in our last week of class, and I look forward to speaking to all of you in our live sessions.